review for Chapter 1 exam. So we're wide open to questions that you might have. I can ask you some conceptual questions. I can ask you this one?
Yeah.
Okay. The density of water vapor at 327.6 atmospheres. All right. Determine Vm. All right. So now, some questions, you need to read into them a little bit. When I read into this, what are they really driving at? Determine the molar volume of water. Okay, so after this Vm and the compression factor, Z. And then part B, calculate Z from the van der Waals equation. So, and they give you the little constants. In that part A, so I guess technically in part B, you call it a van der Waals gas. That's pretty much how you'd identify this gas. Its equation of state is the van der Waals equation. And you get a Z. Part A also wants you to get a Z. What are they implying? What is the equation of state for part A? Is it a van der Waals gas? It's an ideal gas. In part A, the equation of state is the ideal gas law. And that's what I mean when you have to read into this. Because they want Z twice. So they're not going to ask. You get the same answer if you assume it's a van der Waals both times. So part A, they're assuming this is your equation of state. Bless you. Right? Well, how do I get Vm out of that? Volume divided by little n. So my molar volume would be RT all over P. Okay. Did they give us enough to do this? Where's the P? Where's the pressure? Oh, there it is. 327.6 atmospheres. And they gave us the T. Okay. Now we could have made our life much more difficult, but we really didn't have to. We could have used this, and you could have said, "Oh, I assume the volume's 1 liter. Figure out the number of moles." Right? But again, you have to use the ideal gas law to do it, and it would work. You can do it that way. In fact, that's what was going through my brain at first, but then I just started writing PV equals nRT and said, whoa, all I need is RT over P. Okay. And then in part B, now you have to write down that whole, they wanted Z.
Yeah, they wanted Z. I just saw that.
Oh, shoot.
They want VM and Z.
All right. So Z, how do they define Z? nRT over PV, or is it the other way around? Let's go back. Where's our equation sheet? PV M over RT. Okay. I don't even see it. Oh, there it is. PVM over RT. Okay, so then you calculate your Z. Okay, for part A. And then in part B, calculate Z from the van der Waals equation of state. Okay. They give us little a and little b. Where's our van der Waals equation? There it is on the bottom, right? So what do they want? Z is Z. What's going to change? What's going to change? R can't change. It's the little a and little b mess with what, according to the van der Waals equation of state? Pressure, right? You plug in a little a and a little b, right? And it'll mess with your pressure. So what we're really doing here, I guess, calculating Z, so that's this one. I can write it over here. Okay. Calculate that van der Waals pressure. Right. Okay. Because that's what I would do. Because you can't use the what else could you do? What would be the other option? That's what I would do. Let's see if that's what I did to get the answer in the back of the book. Number 24. Yeah, because the van der Waals equation of state gives you the right, well, gives you the van der Waals pressure, right? The pressure predicted if it was a van der Waals, follows the van der Waals equation of state. So did we ever even need that bloody density? I don't think you ever need it, right? What are you going to use for molar volume for part B? Yeah, the molar volume that you had. Okay.
Dr. Smith,
Yes.
whenever you calculate the VM from how you have it, you get a different answer in the back of the book.
Watch your units. What units did you use for R? Which R did you pick?
The liters over.
Oh, you did the .0821. Okay, then you should end up in liters. Pressures and, yeah, that should work.
You got .194, and in the back of the book it's .1353. Isn't that what you got?
Yeah, I got .194.
No, you got
Oh. Yeah, I got, what is it?
It's .135 in the back.
Okay, I got .137 on the quiz.
Let's see.
Using what the VM from how you have it, you get .194.
I bet you get the answer in the back of the book when you use the density, right? Why would they be different answers? Assume the volume is, I think, 1 cubic decimeter. And then you know the mass, right? Then the mass is 133.2 grams. I'm trying. They use the idea that it's water, and they're to get the answer in the back of the book. In part A, they don't want you to assume van der Waals anywhere. Because that's the second way to see this. They should have said at the very beginning, water is acting like or is following is a van der Waals gas. If they would have said that, you cannot do this. But they didn't, right? They should have. I never even realized it. This is another one where I need to modify the homework question. Water is acting like a van der Waals gas. So that means, because if it isn't, you don't care whether there's water, oxygen, methane, whatever. I mean, it's an ideal gas. They're not even molecules in the first place. They're dots. They don't care. You get the same molar volume no matter what. In fact, 22.4 liters is the molar volume of everything. So, and under standard conditions. But that's not true. only for an ideal gas, only for something that's dots. So at the very beginning, if you want to get the answer, I'll accept either one, right, for that. But at the very beginning, if this is on the test, I got to change this question. Water is a van der Waals gas. Assume water follows the van der Waals equation of state. That should be the first sentence. And then you have to use the density to get molar volume because the identity of the gas matters. Okay? And then you would have to do it this way to get molar volume. Convert this into, if you want liters, fine, convert it into liters. Convert that into moles, realize it's water, divide the two, and then I bet you get the answer in the back of the book. Okay. Another way to say it would be assume water obeys. What happened to my eraser? Obeys the van der Waals equation of state. That's another way to say it at the beginning. Comma, and then the rest of the question. It would have been much more clear. So I read into it wrong. Maybe you did you do that on the quiz too? Or did you assume that water was... Did you, I guess what I'm asking is, in part A, did you realize it was water molecules actually flying around and not dots? Yeah, well, then you did better than I did. You did what the book wanted. Yeah, that kind of made her leading you. Yeah. Well, I'm not much of a follower. Okay, how about another question? And you can get this stuff back if you want, and then just turn it in before you leave, and then I'll have it in your folder by like lunchtime here. All right, if you want these back? They're there. Any other questions? I'll whip out some. Well, in part A, you don't need little a and little b.
Oh, yeah.
But in part B, you would.
I used little a and little b in part A to get the .137.
Oh, you. In part A, I would just use this to get molar volume for part A. That's grams of water. So you know how many moles there are. And then 1 cubic decimeter, jeez, I don't know. Isn't a cubic decimeter the same as a liter?
Yeah.
Yeah, well, if you didn't know that, how would you convert cubic decimeters into cubic centimeters? Because you know 1 cubic centimeter is 1 milliliter. How would you get a cubic decimeter into a cubic centimeter? Do it dm to cm first. Where does the number go? Well, you could go. You want to go all the way to meters? Fine. Look at this guy. Fine, we'll go all the way to meters. Why is this so thin? All right, we'll go to meters. It's still thick. What the heck? Okay, decimeters, centimeters. Decimeters and meters.
We'll just do centimeters.
It's fine. We'll do it your way. The number goes where? The number that you write in.
1 to 10.
10 decimeters in a meter. Yeah, we'll cube them all at the end. But decimeters are gone. Stupid thing.
Monday.
No kidding. Decimeter.
5 hours of sleep.
All right, meter, centimeter. Now the hundreds. And then, like, they said cube everything. Well, base 10, there's 10 centimeters in a decimeter. But either way it would work. So you get it into cubic centimeters, which is a milliliter. Then don't forget 1,000 milliliters in a liter, right? But I think you're right. If I remember right, 1 cubic decimeter is how a liter is defined. If you remember that. And any other homework questions in chapter 1? If not, I'll see how much of this conceptual stuff you know.
We need to know the z is less than 1, greater than 1 stuff, right?
Oh, that's conceptual stuff. Z is less than 1. That means, well, first, if Z is 1, what's going on? It's behaving ideally. If Z is less than 1, it's not behaving ideally. What forces dominate? Attractive forces dominate.
Not the ugly ones.
The only way I remember that is I remember the hydrogen plot skyrocketing above the Z. Like, this is 1 for Z. The hydrogen's always above it. Protons, all they do is repel. All right? Hydrogen's always above it. Z bigger than 1, repulsion. So what were the conditions where a gas acted ideally? If you're going to use PV equals nRT, you'd really want what conditions? Low pressure, high temp. Both combined would be even better.
Yeah, I was going to ask you, is it possible to have that? A low pressure and a high temperature?
Well, they're working against each other, but yeah, why not?
All right.
Suck out all the gas. What is STP?
Standard temperature and pressure.
Which is what? 1 atmosphere.
273.
1 atmosphere is 760 torr. And what's the temperature, though? 273 Kelvin, or how many Celsius? 0. 0 Celsius. What's the equation you use? Because it's not on the equation sheet. They say the pressure is reduced by 1/2. What is the new volume?
Waals law.
Well, because they're going to give you all these parameters, right? They may not even give you the number of moles. In fact, they usually don't. And they say, okay, the pressure is initially 712 atmospheres at 2 liters. And the pressure is reduced by 1/2. What's the new volume? And it's not on our equation sheet. I don't think. No, it's not. How do you solve that? This is from the very first day. There it is.
Oh, okay.
Did you hear, Gianna? P1 V1 over T1 equals P2 V2. That's the only way to do it. Okay. The ideal gas law just won't get you there. How about you have a jar of several gases, this thing, right? And we blew some other gases in there and stuff. But water's definitely one of the gases, because there's, you see water in there. But the water's just one little drop hanging on the side. What is the partial pressure of water in that container? It's the partial pressure of water. We're getting into Dalton's laws. You add up all the partial pressures and you get the total pressure. But what's the partial pressure of water in that container? This little drop of water hanging on the side. But it stays there. What is it?
The partial
Well, I'm after a word. There's a table of these things. Vapor pressure. Vapor pressure. Remember, you take any liquid, you heat it up. It boils when it's what equals atmospheric pressure? Vapor pressure, right? It's vapor pressure. So all you need is a little tiny bit of it, and that is. So it doesn't matter how much water you have in that container. The vapor pressure is always the same. It's like density. It doesn't matter how much you have. The density is density. Vapor pressure is the same story. What was the difference between the kinetic model of gases and the ideal gas law? Alice? What's the difference, a difference, between the ideal gas law and the kinetic model of gases? It was the very first theory that we jumped on after ideal equation of state. What did we say the molecules now are? Do you want to remember? There you go. They become steel balls. Okay. Now in this steel ball idea, the collisions were all what? Elastic. That means they generate what when they collide? Heat. It means now that since we have collisions, we have mass, we have collisions, we have volume, we also have something called mean free path. What was that? Say it louder. Distance between collisions. We had something called collision frequency. What was that? Yeah, collisions per second. Okay. We had little c. Little c. Not the speed of light. We had little c. We had little c. It's right here. What was it called? Root mean
Square speed.
Okay, now that's exactly right. Root means square speed. Now what does it mean? Say it in language, in layman's terms, so that you can actually calculate it. Like it's cars. Square root of the average of the speed squared. Yep.
Speed.
Um,
They're all there. All the words were there. Not exactly in harmony.
we have an equation R equals n sub a k. What are all those variables? Yeah, it should be on that equation sheet. Yeah, there it is. R equals n sub a k. K, what was the name of the constant for K? Boltzmann Constant. What's Na? It was what? Number of moles of gas. You look at the equation next to it. What's the little mu, m1, m2, what's that stuff? Mu is reduced mass. What's the purpose of it? Why? Because the steel balls, that's right, there you go. We're connecting the steel balls. They're flying through space. Each one of these guys have a mass. They don't have to be the same thing. They couldn't be, but they can, all right? You want to use Newton's laws. You want to use F equals ma, whatever. There's little m kinetic energy. Little m shows up everywhere in all these physics equations. You can't use, which one do you use? What did you plug in? For all those Newton's laws, all those physics equations, what do you plug in for little m in this problem? You know, these steel balls connected flying around through space. You just add up these two masses and plug that in? You don't get the right answers if you do that, because all this stuff is spinning and rotating around its little center of mass and stuff. What do you have to plug in for the mass? You plug in reduced mass. Right? You plug in reduced mass. Yeah. So you have to, you know, take 1 over m1, 1 over m2, see what the answer is, flip your final answer. Yep. And watch your units. What else do I have here? And you got into I think we said, but what's the compression factor for ideal gas? It's equal to 1. Then we got into this idea of gases, and we're sitting there heating them up, or we're trying to keep them at the same temperature. Yeah, I think that's what we were talking about. We took a gas and we tried to keep the temperature the same, and we slowly compressed it, so the volume went up, right? So as you monitor the volume and its pressure, make a little plot, like here's pressure, here's volume. Make a little plot. That's called a what therm? Isotherm. And at some point along that isotherm, you know, you compress it, pressure goes up, compress it, pressure goes up. It makes a lot of sense. All of a sudden it flattens out. And you're compressing it, it's not pushing, I mean, it's pushing back, but the pressure isn't changing. You keep pushing it down, oh, what the heck? Right? The pressure's not increasing. It stays flat. What was going on? It's turning into a liquid. That's what was going on. And then, okay, so then you get your isotherm, you keep going higher and higher temperatures. And that always happens. It flattens out sooner or later, it turns into a liquid. But then you try this other isotherm. You reach a limit at some point where you hit this temperature, keeping it constant, cranking down the pressure, reducing the volume, but you never get the flat part. Right? It stays a gas. Well, it's not really a gas. What is it called? At that point, where it's a critical temperature, and what is it? It's not a gas anymore. Is it too dense or not dense enough to be called a gas? It's too dense. Things have so much kinetic energy that they just can't stick together and make a liquid. Yet it's too dense to be called a gas. They call it a supercritical fluid, but I don't think we use that word, did we? Oh, we did?
It was in that video that
Oh, okay. According to the principle of, van der Waals equation. Would you get better answers in general with a van der Waals equation or the equation of state? Yeah, between the ideal gas law and the other equation of state, van der Waals. Which one should give you better answers? Better meaning you actually go into lab, or you have a tire, and you measure it, the pressure is 65 psi. Well, dang, Michelin doesn't want to be sitting there filling tires to do all these experiments. Let's get some theory done and test it on the road instead of doing all these manipulations with these tires. It's going to take forever. So let's do some stuff in lab, in theory. Calculate some stuff, make some predictions, see what the effects are. Which one would they want to be using if they only had those two choices? Van der Waals or ideal gas law? Which one? I would say two, right? It's supposed to. Why? Why should van der Waals give you better answers?
Because gases aren't actually just dots.
Yeah, but where do you see this in the equation? It's still a math equation, right? What makes it better? You're getting the assumptions, but why would it be better? It has
The coefficients.
it has some constants. What did Smith call them? What factors?
Compression.
Just an F. It's not a dirty word.
Fudge factors.
Fudge factors, right? You plug in these little numbers, and you get true answers for that gas. You have to look them up for that gas. That's why it's better. It has some fudge factors. And you're right. Where are these fudge factors, and why is the form of the equation the way it is? Well, it's like you said. They have some assumptions in there. And then the last thing, well, one of the last, yeah, it was the last thing we left with. And we're out of time. The principle of corresponding states. According to it, two gases are in the exact same state if what? They have the same reduced variables, which are what? Yeah, it's a little temperature, a T with a little subscript R. And that TR was really what over what? Temperature over its critical temperature. Where do you get these critical temperatures? Yeah, some chart. Look it up for that gas. Right. So again, there's fudge factors again, but it works. Okay. So exam on Wednesday. Come by and ask some questions. I'll be glad to help you out. And lab, oh, good. Lab today at 4. It shouldn't take that long, right? If you have a laptop, I would bring it because you can use your software and your stuff. But I think, hold that up one. I think we're just typing this up. We're repeating that.
Yeah, basically.
So make sure that you can use equation editor and Word and what was the other one?
Excel.
Is it graphical analysis or we're doing Excel?
Yeah, just like Excel.
I don't remember. I'll have to look at it. Yeah. So we'll meet across from my office.
Are we going to be like modifying these equations or something?
No, I just want you to exactly repeat that in on the software. Learn how to do it. It'll help you write reports and things.
I know.
So we'll meet in across my office.
Because I'm asking for his help and I'm leaving you alone.